Okay, so all I'm going to do here is I'm going to do some sound questions. This is kind of the way things roll the rest of the way from now until the end of the year, and pretty much in grade 12, right? Not a ton of theory, more and more emphasis on problem solving. So I'm going to show you some strategies that help here. I'm going to start with like the simplest thing. Sometimes I think teachers start too simple actually, and they kind of make things confusing, but anyways. I would also encourage you to remember that your cheat sheet for the test is a valuable tool, although I sometimes think that students put too much stuff on there. Right? Have a little bit of faith in yourself as well. But please make sure that your formulas are right on your sheet. So, having said that, we got an object starting at a position of -6, ends up at a position of +10. Calculate its displacement during the trip. So we are looking for the displacement, which we sometimes call delta D, sometimes called delta X, right? And I realize that's where the confusing part comes, but you do have to sort of be multilingual a little bit. So how do you find displacement? Well, I've told you way back when that it's always final minus initial. It's the final position minus the initial position. And I realize I'm overcomplicating this. Okay? So which one of these is the final position? Starts at a position of -6, ends up at +10. You're right. This one is the final, and that one is the initial, right? Sometimes you're going to have to read it a couple times and just sort of work through it. Don't be in such a rush. So this is really, I'll just get rid of that delta x. This is really just 10 minus -6. Don't forget to subtract the -6, right? It's subtract. And that would just be 16 meters. And if you want to put a plus sign in there and indicate that's fine. If there's no sign, it's assumed to be positive. That's it. Like, that's as easy as it gets, right? Like, that's like grade 10 intro stuff, which you guys have done before, right? Yeah. Okay. Object moves from a position of +10 to a position of -13 in 7 seconds. Find its displacement and average velocity during the trip. So we're again looking for the displacement, and then we're looking for average velocity, or V bar. Remember, the bar stands for the average. We're going from, this is my initial position, this is my final position, and the 7 seconds would be the time. Now, some people might like to write it out. If you're one of those people, you go right ahead. If you want to write out xi is equal to 10, and xf is -13, and so on, that's fine. You go ahead and do that, if that helps you. Okay, so to find the displacement, final minus initial. The final was -13. The initial was 10. So -13 minus 10, which is -23. Should we put units on our sort of what I call intermediate steps? We should. I don't get too excited about that. But I do get excited about units not being on the final answer. Okay? Average velocity. Now, what's the formula for average velocity? Distance over time, or displacement over time, technically. Right? So that's going to be this number that I just came up with, -23. We're going to divide by 7, and we're going to get 3.3? 3.3 what? Meters per second. Did I do my rant yet about significant figures? Did I talk about that? No? Because usually I get someone asking right about now, how many decimal places do you want us to round to? Go ahead.
How many decimal places do you want us to round?
Excellent question. Usually what I say is one more than what is given. So like here, these are both whole numbers, so I would go to 1 decimal place. If your givens have decimals in them, although I guess technically they've got decimals there, don't they, right? then I usually say one more. I don't get excited about rounding. I do prefer that you round properly. We should probably have that down.
Can you go?
Sure. So I'm going to put a number on the board and you're going to tell me about rounding. Oh, it is negative. Of course it is, yeah. It's negative, right? Of course it is. Okay, let's talk about rounding for a second. Completely aside from problem solving, let's talk about rounding. Did I do this yet with you? I can never remember. No? Okay, so if you were to round that, would it be 3.4 or would it be 3.5?
4. 3.4. 3.5.
We have some disagreement. One of them is right.
3.5.
Okay, hands up. Who says 3.4? About 2/3 of you. Hands up who says 3.5? You do not. You do not. Did you do this? Did you say, oh, well, that makes that a 5, and right? Is that what you did? You do not do that. That is not proper rounding. If you're rounding to 1 decimal place, you simply look at that, right? If you think about a number line, right? There's 3 and there's 4. 3.44 is going to be like there, right? It's to the left, right? So I mean, then you're going to take that 3.4. If I said round it up even more, then you can go 4.0. You can't do that, right? Okay? You only go one, that you do not go all the way back and go back like that. Now, I think that there's a teacher somewhere out there that's teaching kids to do that. Were you guys ever taught that? To go like all the way back and go backwards like that? No? Yeah, don't do that. Don't do that. Okay, let's do my rant about sig figs. I should find like a video on sig figs. You only have one. Find the time required to travel 150 kilometers at a rate of 80 kilometers per hour. These are exactly the same kind of problems you did yesterday. Now they're just written out in words. Find the time required. Solve for t, time. The 150 kilometers is our displacement or distance, right? Sometimes it's not going to come out and say the displacement is. You're going to have to read it. Okay? At a rate of 80 kilometers per hour. Sometimes you have to figure it out from the units. 80 kilometers per hour, that's going to be the velocity, isn't it? Right? So, yeah, unfortunately, there is some more reading involved here. We're looking for the time required. So the formula, V bar equals D over T. Remember some of the things we talked about yesterday? Do I want you to write the formula, do you think?
Probably.
Yeah, I do. And it's not so much that I'm a jerk, or maybe I am, I don't know. I think that if students write the formula, well, A, they start to memorize them more and more and more. Okay? And it helps guide your thinking as well. So I still write them, even when I'm doing my answer key, even though I know I'm the only one looking at it, I still out of habit to write the formula. Okay? I would encourage you to do the same. So that's going to be 80 is equal to, what over what? 150 over t. Okay, and here's the problem that we covered yesterday, I hope. How do I solve this? The t and the 80 switch places, and I really hope everyone can do that. Notice how I've got my equal signs all lined up.
1.875.
Thank you. 1.875? 1.875, and that would be what unit to you?
Kilometers per hour.
Hours. Now, here's an interesting little aside. If it's in hours, if I had to convert it to minutes, how would I do that? Divide by 60? Like, I gotta take 1.8 and divide by 60? Times by 60. Right? Remember, there's 60 minutes in and out, right? So 1.875 times 60. Or 112.5 minutes. Do these appear to be pretty easy? I'm hoping that they do. Are you relieved?
Yeah.
Good. But they'll get harder, don't worry. Okay, this is how many have I got left? 2 more to go?
Yeah.
A ball rolls down a hill with uniform acceleration. It starts from rest and rolls 28 meters in 4 seconds. Find the average velocity, find the final velocity, and the acceleration. So we're going to find 3 things. Down a hill with uniform acceleration. Have they given me any number there? It starts from rest. Have they given me any number there? They have. The initial velocity is 0. It's often the hidden one. Rolls 28 meters. The displacement is 28. The time is 4 seconds. Find the average velocity. Should we label our parts like this? Yeah, we should. B bar equals D over T. Displacement, 28. Time, 4 seconds. 7. I'm hoping you can do that without a calculator. Equal signs lined up. Find the final velocity. Oh, I don't know if I've actually done one like this before. How am I going to find the final velocity? Oh no, we've kind of touched on this. It's uniform acceleration. It's not uniform speed. Your thinking is good. You just applied it wrong. Yeah. It started from rest, though, right?
Yeah.
If it started at 0 and it averaged 7.
So 4 times 3.
4 times 7?
If you're traveling it takes 4 seconds. If you're traveling 7 meters per second. Right? Or you just multiply 7 by 4.
Between 0 and 7 is 3.5.
You're right, but 7's not the one that's on the end. The average is 7. 7's in the middle. 14. Right? We figured it out, but how do you do it mathematically? Well, I don't know if I've ever shown you this or not, but I think I might have. V bar is equal to VI plus VF over 2. Have you seen something like that? I think maybe. When you find the average of 2 numbers, how do you find them? Add them together, divide by 2, right? So the average velocity is the initial velocity plus the final velocity, we divide by 2, right? Okay, so now plug in what you know. The average is 7. This is why writing the formula is important, because you put the right number in the right spot. So the average is 7. The initial is 0. We're solving for the final, and we're going to divide by 2. Okay, I want to isolate VF. I want VF all by itself. I got to get rid of divide by 2. How do I do that? Multiply both sides by 2, right? You guys have seen that kind of thing before? I'm hoping. 14. Now, do I need to write 0 plus VF? 0 plus, just right? So it's going to be, yeah. Or VF is equal to 14. You should be able to go from that step to that step. Like, can you do this bit in your head?
Yeah.
You should be able to. Little bit harder, but not too bad. Find the acceleration. What's the formula for acceleration? Okay. Which velocity, Jason? Jason says this. Nope. It's the change in velocity. Now, do I have the change in velocity? Do I have delta V anywhere up there? I don't see it. I got the initial, I got the average, I got the final, I don't got the change. Here's where I'm at an advantage. You guys have to use a pencil and the eraser part. Whoopsie, I guess I have to erase. I can just move it over because I just realized that I have to find this one. VF minus VF. I got to find how much the velocity changes. I got to find delta V. Yes, I know I made you write something down, then you have to erase it. I'm sorry. You'll get over it. Final velocity is 14 minus 0. Oh, it's just 14, right? Is it? It's just 14, is it not? Okay, let's finish this up, and then I got a question for you. So that 14 goes up there. What was the time again? 4. The acceleration is 3.5 meters per second squared. Actually, I got a couple questions that come to mind. I'll pause for a second. Is the delta V always going to be equivalent numerically to the VF? How not, Colby?
You just got lucky and had zero.
Just got lucky? Oh, so it only is when the VI is? 0, you're right. Actually, the VI is 0 quite often, so I don't know how much luck's involved, because it happens quite a bit. But you're absolutely right. I want to make a note that VF is not necessarily equal to delta V. VF equals delta V if VI is 0. Right? If the initial velocity is 0, then the VF and the delta V are the same. Does that make sense? Good. Because they won't always be that way. Now, I noticed when I marked your test that there's still a lot of people that aren't really sure about what acceleration means. So let's just take a moment to review that, because it's probably a good thing to talk about. So if I'm accelerating uniformly at 3.5 meters per second squared, that means that every second the speed increases by 3.5 meters per second. Every second, the speed increases by 3.5 meters per second. A lot of people on that test wrote things that were similar to the object goes 3.5 meters in a second. That's the velocity. That's not the acceleration. Acceleration is how fast you're speeding up. Remember the car and the motorbike and the plane? Which one got up to speed really fast? The motorbike. It sped up really fast, but the plane was really, really, really fast. But it took a while to get up to speed. That's the difference. Would you like to try one on your own? Say yes. An object has an initial velocity of 1 meter per second, reaches the final velocity of 12, 3 seconds later. Oh, look at this. They made a little trick there. They put the word 3 instead of the number 3. Watch for stuff like that. Find the acceleration of the body during that time. So we got initial is 1. We got final is 12. Do you have to write it out? Not necessarily. You can just put little, write the letters up top there. 3 seconds later. Okay, so to find the acceleration, we're going to go delta V, VF minus VI all over T. Oh, hang on here. That's not right. What am I doing? So that's going to be 12 minus 1, or 11. A equals delta V over delta T. That's going to be 11 over 3, which is 3.6 repeating, right? 3.67, I guess. Meters per second squared. Are these easy?
Yeah, once you know them.
Once you know them, right? Takes a little practice, you guys. Trust me, they get a whole lot harder. And we're doing projectile motion in grade 12. It's 7 steps, right? It's 11 steps. Okay? I'll get you there. But first, you got to do some simpler ones. Why do I have so many extras? I'm not saying that. I have 3 extras. That's a whole tree. Right, you're on the recycling. Here's a pseudo logic for you. You guys probably know what the carbon cycle, right? No, we breathe out carbon dioxide, we're burning fossil fuels, and put carbon in the atmosphere, right? Where is it? Did I show you that video where a tree gets mass?
No,
Every
it's
time
Did we watch it?
What video?
You guys really watch science videos, no?
I feel like we worked good. I enjoy biology.
Yeah. Where does a tree get its mass from? Where does it come from?
Our breath.
You're telling me that those big giant trees out there in Kerr Avenue literally pulled all of their mass, all their stuff out of thin air? Photosynthesis? You're absolutely 100% right. So if you use paper, right, and you kill a tree, well, at least nowadays, when they chop down a tree, they actually plant a tree. So is chopping down a tree and planting a tree, which then has to pull carbon out of the atmosphere, is that a good thing?
Yeah, a little.
Or should we just leave the trees where they are? Because I would argue that a growing tree needs more carbon than a mature tree. So I think using paper is good for the environment.
Maybe it's the young tree.
Maybe. I'm not saying I agree with that, I'm just interested in the logic. I have solutions here, would you like them? Yeah? Oh, I think these are state. Yes, they are. Right. I have a limited number of solutions here. Should I just throw one on every table, or should I just let people come and grab one if they want? When they run out, they run out.
One on every table.
One on every table?
Yeah,
Those are the answers. These are the solutions.
Yeah, I'll get this one for you.
I'll throw one on every table and you guys can fight over it.
Who's around the back?
Those are the answers. These are solutions. You know the difference between solutions and answers? Yeah. Are you going to draw up my grade and science? So I gave everyone solutions. If you want one for yourself, you can look at back. There's a link and there's a QR code. I showed you the QR code, right? You done that? Okay, I'll be quiet. You guys practice. Oh, I'm still recording. I don't need to do that.